second speaker of before the tea break session is Sriram Shastry from UC Santa Cruz. And his title is Extremely Correlated Fermi Liquids.
Thank you. Okay, well, it's a great pleasure to be here at the 70th birthday party of one of my teachers, Professor T. Ramakrishnan. And there'll be more in the evening. I'll say a few more words about our long association and friendship. And I'm also very happy to see here other teachers of mine from old days, colleagues, friends, and also some students. So this is really nice. In this talk, I will try to present some results and the ideas behind a set of calculations which I've been doing for the last couple of years. The name, the operational word, is extreme correlations. So in this talk, I will try to tell you what I mean by extreme correlations. And essentially, it's a theory of the TJ model. For those of you who know the TJ model, that's about all there is. It's a way of understanding the TJ model in a way which avoids standard slave fermion, slave boson kind of technology which has overtaken this field. So I completely avoid that by using some alternate ideas. And then I'll talk about this new expansion, this new theory which emerges. This is a formal theory, and it uses ideas from Schwinger. And in fact, I'm really delighted that Professor Rajagopal is here because I actually learned about Schwinger source techniques during my PhD days. I was too lazy to get the factors in the Feynman diagrams right. So I was always making mistakes. And then someone said, well, why don't you just do it through the Schwinger technique? It's a whole lot more compact and you never make mistakes. So I took out Professor Rajagopal's old PhD thesis, and apparently that stuck. So that's basically what I do here, do Schwinger kind of technique, and by the way, avoid something that Anderson talks about as being brainwashed by Feynman, and I think very rightly so. This is a problem in which the Feynman technique doesn't really work, for reasons which I will explain. And then I talk about this extremely correlated Fermi liquid which emerges, and within this formalism there's a simplified result which emerges, a very concrete result which emerges, and that result can already be tested against a lot of the ITC experiments, and I will show you some comparison with existing data, and you will see that largely speaking the fit is spectacular. You actually see really rather remarkably good agreement between theory and data. And finally I'll talk about some predictions of this new way of doing theory. There is a certain asymmetry which emerges between particles and holes, and this can be tested in experiments, in future experiments. So what do I mean by extreme correlations? Well, if you think of the Hubbard model as a standard model of condensed matter physics, well, we have several well-understood regimes. Weak correlations were used much smaller than T. Intermediate correlations were used roughly of the order of T, where the density function theory works. And strong correlations. Strong correlations is where you'll learn about transition metal magnetism and stuff like that. But then this isn't the end of it. In fact, there's one more step in this hierarchy, I believe, and that's extreme correlations. We use so much bigger than T that it makes sense to start with the infinite U model and then do sort of inverse U expansion. And I believe that high TC systems belong here, and possibly some other systems like the cobaltates, and also possibly some heavy Fermi systems. So the question which often comes up is, you know that U is finite and large, so why should we use infinite U as a starting point? And the answer to that is, roughly, it's a single step renormalization. We're getting rid of the large energy scale first by doing a canonical transformation or something, eliminating doubly occupied sites. And it's fundamentally the same as working with the large U theory, but making really, really sure that you're not wasting precious, prime time, eliminating double occupancy. That's done and dusted, and you're dealing with the remainder. The model which you're dealing with has no further traces of double occupancy, then you do what you can. And further, I would say very important too, the TJ model is in some sense even more fundamental than the Hubbard model, because there can be other starting points which lead to the TJ model. For instance, in the high TC systems, you may have a good case for a 3-band model, which finally reduces to a single band model, and the architect of that, Morris, is right here in the audience. Rice and Zhang showed very importantly that J in this reduction is not necessarily small. J can be a fairly large number, maybe even 1/3 of the hopping T. So this is an independent model which works in the same Hilbert space as the infinite U-Hubbard model, but can arise from other initial starting points. But just to make sure that we really understand what I'm saying, there is a famous Goodsweiler projection operator which we have to deal with. This kills W occupied sites in the entire lattice, and it has a very severe consequence on what we do. For example, the electrons that we create, for example, in our case, we remove an electron, and that electron is not a simple electron, but rather the electron sandwiched by two Goodsweiler projectors, which make sure that there is no double occupancy anywhere in the problem. Basically, get rid of it completely. So the Hilbert space, you've gotten rid of W occupied sites, and there are only 3 allowed configurations. So the resulting model is the TJ model, with the exchange between the spins and electron hopping, which looks deceptively like free electrons, except the Goodsweiler projector enforces single occupancy. So, the sum rules of quantum mechanics are different, and, John Hubbard gave these guys a name. He called them the Hubbard operator. He called them the X operators. We call it the Hubbard X operators. So these are basically non-local operators. So they are very vicious objects. You don't have Wick's theorem and all the standard technology that we learn from textbooks is not applicable to these guys. So this is really the problem. You have to deal with the X operators. The lattice is crucial in the continuum. Even if you have very strong interactions, you can often get rid of the strong interactions through ladder diagrams, or what used to be called as the Bruckner sums. But in the lattice, once you have a Mott insulating state, that's the end of simple physics. You don't have something structurally and fundamentally much more complex. You have an insulating state, you have doping the insulating state, and you have to deal with these X operators. So in other words, existence of the Mott insulating state is a signal of extreme correlations, okay? But we must remember that extreme correlations can also happen very far away from the Mott limit. I mean, you can go as far as 1/3 filling away from the half filling, and yet there is even experimental evidence that extreme correlations are at play. You look at the tunneling density states, they show sloping curves. So the theoretical problem is that of a non-canonical field theory. That's a setting in which, if there's any highly physics in the audience, you would like to know about it. It's a field theory, but non-canonical objects. And how do you handle Goodsweiler projector rigorously without Schwinger bosons or slave bosons and slave fermions? Is there a way of doing that? And it's in a way, I think it's come to the center stage in condensed matter physics. We really have to deal with this somehow. And there are many approximations and numerical attempts made so far, and I think it's questionable to what extent we have learned from numerics in this problem. It's a very hard problem, and I actually strongly believe that numerics haven't done as much good in this particular problem. Generally, I'm a very big believer in numerical methods, but for extreme correlations, I think we need something else. We need a new framework in which to calculate. We need something rather radically different. That's what I'm trying to provide here. So what I'm going to present today is, well, this is a caricature of the phase diagram, and here is temperature, and here is the x-axis. So this is the Mott insulating state. And what I'm going to do is sneak up on the interesting regime starting from here, basically from very large x, which means you have very few particles. You take a lattice with, let's say, a very dilute limit of strongly interacting particles, and then you creep up on here and see to what extent you can approach half filling. So it's in the sense of a virial expansion. The virial expansion in statistical mechanics is basically the most powerful way of doing stat mech. You take few particles, low density, and creep up. And very often the virial expansion stops at some point because it has intrinsic signals of instabilities. And that's really a very safe way of doing statistical mechanics, quantum statistical mechanics. That's what we're going to do here. We'll creep up here. Indeed, there is a point at which things go bad, and then you can't take this particular theory and push it here. I should say a lot of the other works, in fact, Morris is going to talk tomorrow on very interesting and ingenious phenomenology on the very same things, the photo emission, but he's going to work in this side, basically on the overdoped side, and there's some new physical insights that he implements to get an understanding out here. So I'm going to work here and push this as much as I can. So the solution which I'm going to present it can be summarized actually in one equation. So you think of a propagator, electronic, we're looking at a one electron Green's function. So that's what photo emission measures, okay? So photo emission is a direct probe of this object G, K of omega. And with taking some liberties, you can replace the 1 by some number, and you think of a Dysonian self-energy. And that's the standard way in which you would do a theory. But here, in this extremely correlated Fermi liquid point of view, it turns out to be much more convenient to break this into a ratio of 2 parts. There are 2 essentially distinct functions, 2 self-energies, so to speak, which enter this problem. The teacher model does describe in terms of 2 self-energies. So what is psi? Psi in reality is a dynamical spectral rate. And in a nutshell, the whole essence of the TJ model physics is that the spectral rate of the correlated electron is 1 minus n by 2 or something, because the anti-commutator of the electrons is no longer 1. These are not simple electrons, not canonical electrons, but because of these Kurzweiler projectors, the anti-commutator of CNC dagger is like 1 minus n by 2. So basically the spectral rate at high frequencies is less than 1. You lose some weight because of extreme correlations. But if you lose this weight at all frequencies, then you're dead. Your Fermi surface must distort, and you cannot satisfy the Luttinger-Watt theorem anymore. So requiring the Luttinger-Watt theorem to be valid, namely the invariance of the size of the Fermi surface and extreme correlations, can only be possible if you have an intelligent spectral rate, which knows that it should go to 0 at high frequencies, or let's say 1 minus n by 2 at high frequencies, but comes back to an uncorrelated value at lower frequencies. So it's going to adjust itself depending on the frequency you're looking at. And that's exactly what this guy does. Psi adjusts itself in giving you the right weight at high frequencies and leaves the what. Okay, so this loss of n by 2 arises from this anti-commutator being less than 1, and it's a loss of the lower Hubbard band weight at high frequencies. And this is an extreme correlations whole, and this is well-known fact. I mean, John Hubbard knew this a long time ago, and he didn't correct for it in the right way. Therefore, he got an approximate theory, the Hubbard 1, Hubbard 2, and Hubbard 3. All of them get the wrong Fermi surface for precisely this reason. I mean, the spectral weight remains 1 minus n by 2 at all frequencies, including at low frequencies. That's why you lose the Luttinger-Watt volume. So that's what we're going to be trying to do. We're going to learn from the experience and try to do something more sensible. So there are some technical details which I will go fast over. Basically, the technique used is to, as Schlinger pointed out a long time ago, the most fundamental thing in the field theory is the equation of motion. Okay? And in fact, the equation of motion, when you evaluate the propagators in the presence of a dynamical, like a time-dependent potential. Okay? So basically what you can do is work out the propagator of an electron in the presence of a dynamical potential, which couples with the spin and charge densities, which is this object mu. So here is xx, which is like CC dagger, but in the presence of this source term. And if you calculate the time derivative of this g, you can express a linear functional differential equation, because all the higher order correlations can be written as the functional derivatives with respect to the source. So this is the very ingenious and fundamental, contribution made by Schlinger himself. He recognized that this is the way to do a theory with absolute exactitude. And this you can do even for non-canonical objects. So here is the propagator, the time derivative, and what you find here is that, the Green's function has a discontinuity in time. When you have A dagger or A dagger A at 0 time, they don't match the same value at t equal to 0. There is a discontinuity which the textbooks tell you. And the magnitude of the discontinuity is the coefficient of the delta function. It usually is 1. Here, since they are non-canonical objects, you get something less than 1. And this object, gamma, is a time-dependent object. It's time-dependent and dynamical. That creates all the difficulties of the problem. So gamma is a local Green's function. This gamma is basically local Green's function, and this superscript of k is a time reversal in the split space. So this is an exact equation. Mu is the source. Y is like a band structure which comes from just the various commutators, and x is a functional derivative with respect to the source. So x is defined with respect to d, and d is essentially a functional derivative. So that's basically the exact equation of motion, and we're trying to find some way of solving this. Okay, so the comment 3 here is an important one. This is a very toxic equation if you don't take care of the gamma here. In other words, the discontinuity is multiplied here by time-dependent function. And you have to essentially deal with this complexity right away. And if you can do that, then we can have a sensible theory. So basically various techniques to get rid of this gamma have to be invented, and I have found a way which does it very nicely. So let me describe that. So the idea is to think of a propagator as a convolution of a canonical propagator. Little g is always going to be a canonical Green's function with a time derivative such that the delta function is a coefficient 1. Okay? So there's a hidden underlying canonical fermion in this theory, which is little g, and that's multiplied by this mu, and mu is nothing but this intelligent spectral weight that I talked about. Spectral weight which does this dance at very high frequencies is 1 minus n by 2, at low frequencies it's got to come back to 1. So just think of g and mu as, at the moment, rather arbitrary functions, and this is a convolution. B bar simply means integrate over B bar, over the various domains. And you do a few tricks which are all sort of very straightforward, and there's a very handy place where you can learn about them. The PhD thesis of Professor Rajagopal in 1965 from Harvard University. And you can use them and you get closed compact equations. So here's the compact exact equation of motion for this object. So here's the dot product, which means this derivative acts on this, and no more functional derivatives. In other words, functional derivatives have all been absorbed into phi and psi. So phi and psi are essentially the functional derivative. L is basically all the relevant functional derivatives acting upon G inverse and acting on mu. So this gives you these two self-energies, psi and phi. And by the way, at any point in this game, if you get confused, you can throw away mu, say I don't care about mu, and then this theory is basically exactly the Feynman-Dyson theory. So at any point, we can switch off the second hierarchy and go back to familiar grounds. It's exactly the Feynman self-energy expressed in terms of the Schwinger weight. Okay, so then there's a simple answer which says you can slice this equation into two parts. If you think of this entire thing acting on G as a delta function, then basically mu is whatever is to the right. So basically this factors into two equations, and this equation for G is exactly a canonical theory. So bottom line, if you play around long enough, you discover that you can slice this equation into two parts, and you get essentially a canonical theory folded in with a dynamical spectral weight. And yeah.
Things like higher-order Green's function, doesn't that?
Higher-order Green's functions are there because they are generated by this functional derivative. So functional derivative exactly generates the higher-order derivatives. And now these higher-order derivatives act on both pieces, little g and mu. So that's this reorganization we are doing. Okay?
So far there is no approximation.
No, it's exact. This is completely exact. Okay, so a few more points to note is that, I'm actually going to introduce an important parameter called little lambda. Little lambda is actually exactly 1 if you do this theory right. But I introduce this parameter lambda, which if you put lambda equal to 0, this becomes a canonical theory. So basically lambda is something like u divided by t plus u or something like that. In other words, when u is infinity, lambda is 1 approximately. And you can think of a adiabatic sort of motion along lambda as generating the fully non-canonical Woods-Fowler theory starting from the Fermi gas. So this is important because lambda helps you to ultimately recover the Latinger-Ward Fermi surface. At any stage in lambda, if to any order in lambda you can do a theory, it turns out to be a conserving theory, and with that order in lambda, you get the Latinger-Ward volume and you get the right Fermi surface. And as you push lambda to 1, you get the full theory. Right, the original Hamiltonian does not have a U, it only has a J. The Hamiltonian doesn't even have a lambda. So what I'm doing is I'm introducing a lambda as a bookkeeping device. If you don't like lambda, put it equal to 1. Okay? But since I need to develop systematic methods for devising conserving approximations, I need to worry about lots of things like conservation laws. I need to worry about word identities, stuff like that. So lambda is a very convenient device. So to any order in lambda, you can say, I'm going to do theory to order lambda squared. It gives you a finite set of equations. And then there is a bookkeeping, you can look up the word identities and it satisfies them. You can prove that. And then, so you can go to that order, then go to the next order, and so on. So, possibly. I mean, the Woods-Fowler projector is a static object, I mean, it's not guaranteed to give you any dynamics. So in some sense, this lambda is making its entry in a far more profound place. It's entering a theory which gives you the full dynamics of the model. But indeed, in the static limit, this has the same, convenience factor as the Woods-Fowler G. Of course, Woods-Fowler was finally interested in relating G to U. He did that, in his variational calculation, and Brinkman Rice, they showed how to complete that. But here, for me, this lambda is slightly different because I want to satisfy the dynamical conservation law. So I think, for me, the word identities turn out to be very important. So for that, this lambda.
You have to set some identity.
Yeah. Exactly. So here, you see, some people I don't have to explain. I think he could have done this before many years ago. Okay, so there is a double Ward-Takahashi identity for G and mu, and we can do various things. And I just want to say one thing, that experimentally, even very far away from half-filling, this tunneling data shows you that extreme correlations are at work. The tunneling conductance is not flat in the normal state, it has a symmetry. So I've actually said all these words, so I'm going to just skip that. But extreme correlations occur everywhere in the system. This is Yazari's data. Yeah.
I think their volume is only one.
Yeah.
And in that case, how does the second vertex?
No, actually, so Latinger-Ward volume will arise when you look at one of two things. You could look at the real part, the physical Green's function, and say, where does that change sign? And to get the real Green's function, the real part, the full Green's function, you have to take convolution of the two pieces, G and mu. So that's why both the vertices have to be well behaved and to be consistent with each other, so that the physical G is well behaved. Okay, so look, there's a so I'm doing well in terms of time. So there is an exact set of equations which you can write down. So the two self-energies are written in terms of convolutions of two vertex functions, lambda and u, with something which looks like energy. The energy is a Fourier transform of the hopping and J. And in K space, the physical Green's function is just a simple product of energy and mu. And I should say that Phil Anderson has been doing this hidden Fermi liquid theory for the last couple of years, and Phil has been very excited about, also explaining, it turns out, the same data that I'm going to work with. So I had a very, shall I say, interesting discussion with Phil on these matters. And Phil told me many times that actually I was just doing what he had phenomenologically done. It's actually not so, because this is a product, it's a convolution in real space. So in time domain, it's a product. Whereas what Phil is doing is this in this strange Fermi liquid idea, he's doing a convolution in K space. So this is a product in real space. So it's somewhat different, and indeed the answers are also, there are some superficial similarities, but they're actually quite different. So I want to say that the propagator that you get from here has has, it looks very much like a Dyson propagator. Little g looks exactly like a Dyson theory, canonical theory, but there is a second guy, mu, which comes along, and you have to find mu in terms of psi, and there's a set of equations for the psi. So it's a game which you can play exactly the way you do the Feynman theory. And you need a control parameter. So I would say lambda is a control parameter, and interestingly, and actually post facto, it turns out that lambda is the same as the density. So this virial expansion idea is what is governing this. So expansion in lambda also turns out to be an expansion in the particle density. So second order is like a second order in the particle density kind of expansion. So there are two particle number sum rules. G itself satisfies the Leffinger volume, and the psi factor which determines mu simply adjusts itself in such a way that you don't distort the Leffinger volume anymore once it is set by the canonical theory.
G has a constraint.
Pardon me?
G has a constraint.
Yeah, this is the constraint of G. This is which is what sets the chemical potential for G. So chemical potential itself has to be factored into two parts, and that's a detail which I am not presenting here. So anyway, look, the point is it's an exact formulation, and you can do this to any order in lambda, which you can get either yourself or a talented postdoc to work on. And at any order in lambda, you can do the theory. We are still working on the second order numbers. So little lambda, I repeat, is an adiabatic parameter invented to make contact with a Fermi gas, and ultimately you will set lambda equal to 1. Yeah.
Since you want to develop a formulation which connects the and equal
To Fermi gas.
Fermi gas,
Yeah.
and equal to 0 is that ideal point. Why not you add itself as a parameter?
Yeah, well, I would say it's a good point, and I would say that m doesn't make a friendly presence in the equations. Lambda makes a friendly presence, and you can trade lambda for n, and mathematically it's more convenient. Yeah.
But you are putting it by hand.
I'm putting it by hand. So every time there's a density factor, it occurs with a lambda factor. That's what the combination is. Every time you generate a density factor, it comes automatically with a lambda factor. Yeah. So I will then actually start with trying to solve these equations to lowest order in lambda. So the lowest order in lambda, phi looks like GGG times the product of energies, and psi is GGG multiplied by energies. And this GGG business is nothing but the analog. And if I do a Hubbard model, for instance, then the self-energy to order U squared is something like G, right? So this is exactly the analog of the second order self-energy diagram, and the role of the interaction U squared is played by these E's. And notice that psi has got one less energy factor, and this is dimensionally necessary because psi is in the numerator, is dimensionless, whereas phi is a self-energy, so it really has dimensions of energy. So that's why it misses the energy factor. And the simplified approximation you can make is think of psi and phi being proportional to each other, being interesting functions of omega, but independent of k. And that's a very natural thing to assume. In higher dimensions that could be the case, but I'm going to use it as an engineering approximation. Think of dropping the k dependence. And then the whole thing collapses into something very, very concrete. So psi is proportional to phi, and the proportionality constant is this number delta 0. So with this assumption that psi and phi are proportional to each other, the claim is that this general function becomes, this function becomes something very simple. It becomes, so here is the spectral function for the physical electron. So here, this gamma over gamma squared plus epsilon squared, it's a Fermi liquid part coming from the little g. And this, the remainder is essentially a constant, n squared, and z is energy, the particle energy, and x is the frequency. So you see, here is a non-Dyssonian spectral function. There is a spectral function which is remarkable in that the frequency appears also in the numerator with a very precise coefficient minus 1 over delta 0 times n squared by 4. Epsilon is basically the energy, z minus x, or something like that. And gamma is the width, the imaginary part with self-energy of the canonical theory. So rho g is basically given by this gamma over gamma squared with epsilon squared. And delta 0, this is the only extra parameter which extreme correlations brings into this game, and that's determined by the sum rule that the number of particles that this contains is the sum of the number of particles this contains. So this delta 0 is determined completely in terms of the Fermi liquid. It does not introduce any new parameters. That's the remarkable thing about it. It's a very lean theory. It doesn't bring in lots of parameters. Just one more parameter, delta 0, and that's linked back into the properties of the Fermi liquid. So,
Integral on x.
pardon me?
Integral on x, then that's the sum.
The integral over x and z times the Fermi function.
So its sum is not.
Yeah, that's right. This is the only extra piece that I got. I mean,
We write in two what the vertices and
no, actually it takes a bit of paper to do that. So maybe I should just postpone this. I'm happy to show you the details. It's a really two-line algebra, but basically a trick with partial fractions. Basically the same self-energies in the numerator as in the denominator, then add and subtract the frequency, and then we get a constant, we throw that away. Essentially partial fractions gives you this answer. Okay, so to summarize, we have to remember that the exact formulation gives you the spectral function, which is the canonical theory, times frequency in the numerator and these two guys, which can be k and omega dependent. But in the most simple theory, this is k and omega independent and eta is 0. That's the simplified theory, and that's what we're going to work with. So the non-Dyssonian, non-Fermi liquid line shape we're working with looks like gamma over gamma squared plus epsilon squared, like a Lorentzian, multiplied by z minus omega. Strangely enough, Freeman Dyson also thought about ESR during a sabbatical in Berkeley. And Kittel posed him the problem of explaining the line shapes that they were finding in ESR. And Freeman Dyson came up with a line shape which is again exactly this. He did get an X in the numerator. So there's some serendipity, some cyclicity in physics. Things keep coming back. Okay, so all right, so here's a very simple model for the Fermi liquid. You can take the Fermi liquid as basically x squared plus omega squared, which is what a Fermi liquid should do at low frequencies, and you add to that a cutoff, which at high frequencies kills it. So basically, this is omega squared plus temperature squared, and that it rolls off at some high scale. So that's this part. When you add to that at eta coming from elastic scattering. Eta is necessary because we're talking about systems which are not necessarily pure. There is elastic scattering, and eta plays an important role, which I will explain in a minute, one more time. It distinguishes between two different kinds of RPS, the synchrotron source RPS and the laser RPS. It turns out that these require very different values of eta. So you need this parameter eta in order to understand the two kinds of RPS which is seen. In any case, eta has got to be there. So this is the Fermi liquid gamma, and this delta 0 is calculated from the sum rule. So this theory has just two parameters really. Well, one is eta, which is elastic impurity scattering, which is an external parameter. And lots of people have talked about it, including Elinor Abrahams and Chandra Varma. They talked about eta in the context of the marginal Fermi liquid theory and tried to explain. Right. And then there is C phi, which is the strength of this cutoff, and omega C is the high frequency cutoff. So basically, it's a very lean theory with three parameters. And now here's some fitting. So let me just show you what happens. So this is there are two PRLs that came out in July. One with Gihon Grion that compared the BISCO data, BISCO and RPS data along the modal direction in the normal state, which is extremely robust. Many experimental groups have seen very similar data. And so here are the 10 values of K at which you see these are the K values. And here is essentially the synchrotron experimental data from composite data, and the red lines are basically our fits. So fit them exactly, okay? So amazing accuracy. This is a particular value of eta. So eta is the only parameter which you have to play with, and you pick one eta for this whole experimental setup, and there you are. You have all these guys fit with very good accuracy. And here's Gihong's VSCO data, which is also very similar to the composite data, but at different temperatures, and it also fit. So here's the theory versus experiment, and that's just these three parameters. And here is lanthanum, strontium, copper. This is data from Fujimori and ZX Shen. This even has a rising term to the left. And the rising term to the left, again, is nothing but a signature of this peculiar line shape. This line shape has a minus x. And you see, as x becomes negative, this rises. So this line shape typically rises to the left and then decays. And that the lanthanum system seems to be having in its data right away. And the blue curve, so the red curve is what we get from the same parameters which fit VSCO. In other words, VSCO and lanthanum, strontium, copper apparently look very similar from the point of view of this coarse-grained picture. But if you want to do slightly better, you can tweak the parameters and even fit, to great accuracy even this rising term. And the typical Fermi liquids don't have it. Fermi liquids have a vanishing antisymmetric part. And it turns out Casey Anderson also has an antisymmetric part, which is almost identical to what I have. So at the end of the day, it turns out that there are new experiments which you can do by looking at the delicate antisymmetry in K and omega around the 0 point. And this would give you basically two sets of theories. I mean, one would be consistent with it, one would not have the antisymmetric part. And I think at the moment it looks like many of the standard theories don't have an antisymmetric part, whereas the Anderson-Casey calculation and what I have done also has an antisymmetric part. Now, Fermi liquids, so what I'm describing to you is an extremely correlated Fermi liquid. The thing to remember, there is still a Fermi liquid generically. And it fails to be a Fermi liquid only at special densities. So there is a possibility that this theory breaks down at as we approach half filling at some particular density. And in fact, we see signs of that already. I know the mechanism for that. That's where you begin to see linear resistivity and stuff like that. We don't have a theory of that yet, but we see it coming, as we take this virial expansion in March and on. So maybe this is a good time to stop and take some questions. Thank you.
Right, and where would that be with the parameter values that you've taken?
Look, I don't have a DD in the audience. I should show them this picture. So here is the anticipated me. So here is the angle integrated photo emission spectrum. And what I'm saying is, as a function of density at different densities, you always see a rising curve to the left. Okay, in other words, at more or less all densities, you see a rising curve to the left. As you approach half optimal doping, the curve rises. And there's a very interesting prediction which I should try to get you interested in. There's a little dip here. There's a minimum at a scale which I can tell you. That scale is the scale of the waterfall in the angle resolved emission. And that's an inevitable part of this theory. And if you do STM tunneling, STM is unfortunately doomed by matrix elements. So it's not very sensitive to the nodal direction. But if you could do a STM which was not bothered by this form factor, you would actually see an asymmetric thing, but with a small proximity of the chemical potential, you would see a reversal. And there's a very good reason why this happens, and I can explain that. And that's connected to this dip here. So angle integrated photo emission does have a linear rise, and it has a linear minimum. Yeah. Yeah, I just took. Right, so for me, so I did this calculation in this simplified model, right? In the simplified model, my delta is K independent. And basically that gives me the same delta at all points in the Fermi surface. So presumably this overestimates the tendency for a linear rise. So you're absolutely right. If I do a pseudo gap, pseudo gap corresponds to a k-dependent delta, and that would reduce the magnitude of this thing. But I would say, inevitably, there's a claim to be made here. So if you look at this, there is a very good reason, which I think I explained to you in Augsburg, why there's got to be a rise in the middle. There is a quasi-particle part of the auxiliary Green's function, and that basically is peaked at a what's up there? This rise, you mean? Here, this rise. Yes. Yes, it will. Right. That's right. Yeah.
I'd like to ask a question. You did this to second order, and you got an asymmetric part. Presumably, if you did it to third order, you get a symmetric part?
No, it remains asymmetric due to structural reasons. It's really rather very simple. Look at, I think this was another question also. You have something like, let's say a self-energy divided by some constant, divided by z minus k minus self-energy. Then basically what we're saying is, think of this as sigma plus ek minus z plus z minus ek. And write this as, so basically ignore this part. And this is the only thing that survives. So it's effectively 1 minus n by 2 divided by constant divided by z minus ek minus self-energy plus some constant. The constant doesn't contribute to the imaginary part of the self-energy. It doesn't contribute to spectral. So essentially to all orders, this, it will be a symmetric. Yeah.
Do you have any idea about the next order term, how much it is?
In Lambda? In Lambda, how much it does? I don't actually know. It's a very obnoxious calculation. It's a numerical calculation which should have been straightforward, but turns out to be rather obnoxious for various reasons. Yeah.
So, if I understood you right, you were saying that the difference between synchrotron and laser RPS is that different samples were used in which there was different impurity scattering?
No, what I'm saying is the eta value is different, and the explanation for this so-called explanation is that in the case of synchrotron data, the exiting photoelectron is basically at a much higher energy. So the exiting photoelectron is sampling a very small region close to the surface. So it's pinned to the surface, whereas in the laser RPS, the exiting photoelectron is sampling the entire bulk. So what I'm saying is the surface is contaminated with disorder. So surface layers would see much more elastic scattering. So this requires basically an understanding of the mean free path of the exiting photoelectron as a function of its energy.
In view of the late time, I think we should continue the discussion outside and thank the speaker. We return back at 3:30.